So we're just going to talk a bit about its formal convergence guarantee, and I may very briefly go through a sketch of the proof. If you're interested in seeing more details, then please take a look at that Lee paper. The assumptions that we're going to make to get a convergence rate for Proximal Newton are the same ones that we've basically made for Newton's method applied to G, which are that G is sorry, these slides are littered with typos. I am not not been as careful as I should have been. This should say that the gradient, the Hessian of G has smallest eigenvalue m and largest eigenvalue L bounded over all x. So I wrote grad up there. That doesn't make any sense. It's on a matrix. But this is the standard assumption we make on G in order to apply Newton's method in theory, so that we have, G is strongly convex and has a Lipschitz gradient with parameter L, or in other words, its Hessian is wedged in between two scaled identities. And furthermore, that this Hessian matrix itself is a Lipschitz function with parameter m. So those are the assumptions we made for Newton's method, if you recall.
I don't know why we do not require strong convex in the first order method, but always assume that in the second order.
So I think you asked this when I covered Newton's method. It was this. So the point is that if we apply Newton's method, then we are assuming that the Hessian is invertible. Otherwise, it doesn't make sense to apply Newton's method. So we have to assume strong convexity. Otherwise, the Hessian being singular is something that we wouldn't be able to handle with Newton's method. We would also, in that case, apply quasi-Newton method. So first-order methods can be applied more broadly than Newton's method. So for first-order methods, we had different types of results. One that assumed just a Lipschitz gradient, and the other that assumed that and strong convexity. So okay, so that's the assumption we make on G. And it's also assumed that the proximal operator of the scaled proximal operator corresponding to the Hessian matrix H of G is evaluable. I mean, here I said exactly evaluable. So that's because in this proof we assume that every time we evaluate the scaled prox, we get the exact answer. There's no error there. Okay, so that's not what's happening in practice. That was realistic for proximal gradient, by the way, because oftentimes it's like the L1 norm or something, so we get the exact answer. It's not realistic for proximal Newton because we almost never know the scaled prox in closed form. So we have to run some kind of inner optimization, and this particular result is not accounting for that. Okay, so it's not accounting for these noisy scaled proximal evaluations. One of the contributions of this paper is to prove a convergence result even outside of that case. So I think I cite it in these slides as well. So under these two conditions, this one being idealistic, you get essentially the same result as you get for Newton's method, which is that there is some step or iteration number k0 after which proximal Newton enjoys quadratic convergence. So the distance between optimality of your current iterate and x star is less than or equal to the square distance that you were before times some factor m over 2m. So this is the same as the guarantee we had for Newton's method after some point, and it leads to a bound like this, log 1 over epsilon steps to get an epsilon subaccurate solution after k0. So that's what we call local quadratic convergence. Because once we get to that point, k0, then we only require this many iterations, log 1 over epsilon, to get an epsilon suboptimal solution. Okay, but every iteration here, recall, requires a scaled prox evaluation, so that's very expensive. So even though this is maybe only like 5 or 10, that's still sizable in terms of the computational cost. So a sketch of the proof. I'm not sure, I was just looking at this, I'm not sure that that I can give you much intuition for the quadratic bound that you eventually get, it comes from the specific properties of the scaled Prox operator that are proven in that paper. Those properties are similar to those that you have on the Prox operator in the unscaled form, but they're just generalized because of the presence of this matrix H. But the proof is similar to the Newton's method proof in the sense that there is a damped phase, so that in this phase between steps 1 and k0 of the algorithm, backtracking chooses a size that's less than 1. Okay? And at some point, you enter into the quadratic convergence phase, where backtracking is always going to choose t equals 1, because this exit condition is always going to be met, wherever we wrote it down, with v as defined, so that don't change t at all. And once you enter that phase, it's not too hard using the properties of the scaled Prox. And this just comes from this first inequality. This just comes from the fact that the Hessian has lowest eigenvalue m. Okay, if you think about that for a second, this is just directly comes from that fact. These next two lines, which are kind of crucial in establishing this quadratic relationship, they really are specific to the scaled Prox operator. So I think it would probably take me more time than I'd like to go through them, but you can just take a look at the paper to get more details if you'd like. Okay, so overall, similar to Newton's method, but uses some of the elements of the proximal gradient proof as well, because we're dealing with Prox operators. So this is what I'd rather spend time on are two notable examples of proximal Newton methods. Glimnet and Quick are the names of proximal Newton applied to different classes of problems, and they're very popular nowadays for solving those classes of problems. So Glimnet is now a Fortran package that has a wrapper to R in MATLAB. That was written by Friedman and co-authors in 2009. And the idea is to apply proximal Newton to solve L1 penalized generalized linear models. So lasso is a case of that, but you wouldn't use any proximal Newton for that because the loss is already a quadratic. But logistic regression, Poisson regression, multinomial, any any generalized linear model loss, any exponential family loss it handles, and it does this wherever I wrote that down. So it applies proximal Newton to this problem, where this is the negative log likelihood from an exponential family, and in every inner step it applies coordinate descent. So that's the contributions of that work is a very careful implementation of coordinate descent for the lasso problem with a quadratic loss, and the wrapper to be able to solve any generalized linear model problem is proximal Newton. Okay, so we will go through coordinate descent in detail when we talk about it for the advanced topics, but you can have in mind that it is a method that is very specific to quadratic loss with an L1 penalty. Okay, it works very well for that case. It doesn't even apply outside of that case. So we need to do something else, and what we do in this case is apply proximal Newton. So that's at least for statisticians, it's a very popular package. Another very popular method is Quick. It applies proximal Newton to solve graphical lasso problems. So different classes of loss functions and generalized linear model losses. And again, it uses proximal Newton and reduces to using coordinate descent on the inner problems, which are just lasso problems, right? Quadratic problems with an L1 penalty. So some more evidence that coordinate descent is very efficient for the pure lasso problem. You can see it's used actually in both of these methods as the kind of go-to solver in the inner loop. This is also the novelty in this work was that the Hessian is just completely enormous when you deal with a problem whose variable is defined over a graph. So they use some kind of neat Kronecker product tricks, so they never have to really store the Hessian in memory, and they can get away with kind of more reduced computations that don't involve the full Hessian. So these are both very widely used, and I would claim they're close to state-of-the-art for these problems. Now, that's only considering problems that are at the right scale. Like, these aren't going to be state-of-the-art for problems that are so big you can't fit the data in memory, these wouldn't really make any sense there. But at some scale, I would claim these are close to state-of-the-art. So it's just to give you an idea that proximal Newton, when applied carefully and with a carefully chosen inner solver, can be very, very good. So these will do better than, for example, just applying proximal gradient to the problem itself, which is why people tend to use this. Okay, an interesting side note is that proximal Newton requires far less evaluations of the gradient of G than proximal gradient. So that's not something we've considered so far. The gradient was usually considered to be something that is just treated as a constant in a sense in proximal gradient. We just have to evaluate grad G, and so we get it and we plug it into the proximal operator. If evaluating the gradient of G is itself expensive, then proximal Newton is also a good idea, because remember, there are far fewer evaluations of the gradient. If you go back to the definition of proximal Newton, we have to evaluate the grad of G at x, then we solve this inner problem. That's some optimization that we run off and do coordinate descent for, say, or some other fancy method that's specific to quadratic loss. But grad G just stays the same throughout that whole time. And then we make an update and we evaluate x again, grad x again, grad G at x again. We solve this inner problem, say again with our favorite method like coordinate descent or something. But because there are fewer outer iterations, like 15 to 20, we actually don't evaluate the gradient as often. And if grad G is expensive, that's to our advantage for proximal Newton. So let's go through some examples. I took these from the Lee paper. So here we're looking at L1 regularized logistic regression. And we're going to apply proximal Newton with coordinate descent as the inner loop. We're going to apply FISTA, which is just proximal gradient, but with acceleration. That was, remember the name, fast iterative soft thresholding algorithm. So this is just proximal gradient for this problem with acceleration. And a third method called, I guess, Sparsa. I don't really know this method very well, but it's a projected gradient method that operates in a different coordinate system, essentially. Okay, so all these versus proximal Newton. And it's a problem that's not huge, but that's not tiny either. So 5,000 observations, 6,000 features, and x is dense. This is just about the worst case for proximal Newton because the Hessian is dense. So it's a very challenging case for proximal Newton. It would only get much more favorable if the Hessian was banded or sparse or something. So here are two different plots that parameterize the x-axis differently, looking at the suboptimality of the solution, basically, for the different methods versus some unit of computational cost. And this one on the right is time. So in seconds, to solve one of these problems at a particular value of lambda. And this may be fair, it may be unfair in the sense that different implementations may have different speeds simply because the person who implemented them was a better programmer or a worse programmer. That's why we typically don't like to look at time on the x-axis, but it's relevant nonetheless. So with this metric, proximal Newton performs quite well. It was also implemented very carefully by Jerry Friedman. So Jerry was the first author on that GLIMNet paper. He writes code in Fortran that's very efficient. FISTA, I don't remember if it's implemented in C or not, but it's a little slower. You can see its convergence regime is different, and this sparse spectral algorithm is not very good. This is maybe the more relevant comparison in terms of function evaluation. So this is just asking how many times did we evaluate. I think that they counted the evaluations to the loss, G, as well as, oh, I see, sorry. I'm trying to remember what this comparison was in terms of. This comparison, I believe, was in terms of evaluations to functions that are just beyond flops. So not counting flops, how many times do you need to evaluate other functions like the exponential function or the log function, which at some level are much more expensive than a flop. So every time you call exp or log in C or in Fortran or something, or any language, it performs a bunch of flops to get the answer. So this is what they counted, because this was kind of like a notion of computational cost that was just beyond flops. And you can see that Proximal Newton does much better in this metric. And it's because it has to evaluate g and the gradient much fewer times, for the reasons we just said. Okay, so because those are expensive relative to flops, it's going to dominate in this comparison as well. Okay, here's another problem, a much larger problem. So about 500,000 observations and 50,000 features. And the feature matrix is sparse. And this is a better regime for Proximal Newton. Right now the Hessian is actually sparse. It passes on a sparse Hessian to coordinate descent, which only does better with a sparse feature matrix. And it strives in this regime as well. Okay? So those are, I think, two nice examples of Proximal Newton from that paper. Are there any questions about that? Yeah? That may be true. Let's see if I can pull up the right graphic for you. So I seem to have saved the same file twice under two different names. So that's not going to help if I pull them both up. Yeah, oops. Thank you for pointing that out. So I think that what I was intending to show here was that Proximal Newton does well for this larger problem, but relatively speaking, it dominates more so in terms of time than function evaluations, because X is a sparse matrix, the cost is kind of less dependent on g and its gradient. So what you should have seen is a plot that I think you can, of course, please go check the paper, and I'll replace this graphic with the right graphic after lecture. But I think, from what I recall, it was more efficient, relatively speaking, in terms of time than function evaluations in this example. Yeah, that wouldn't make sense that for a problem that's 10 times as large, or 100 times as large, that has the same time. So just from that, you can tell that was not the right graphic. All right, not a good lecture in terms of typos, huh? A lot of typos. Sorry about that. So, OK, we have a few more things I wanted to cover. There's a few practical issues to applying Proximal Newton. The first is inexact proximal evaluations, which we always do encounter in practice. We never really evaluate the proximal operator explicitly because it's not typically characterizable in closed form. So you might ask, both practically speaking and also theoretically speaking, what do we get when we evaluate the prox with an optimization routine? And the examples are, the conclusions are fairly encouraging in either case. So here in this this example, it's a fairly small problem, but with a large feature set. And the authors are demonstrating that if you were to run the inner coordinate descent algorithm for a maximum of 10 iterations versus run it like arbitrarily long for a very long time, that's why they chose a small problem, so they could get close to the exact answer for that inner loop, which is displayed in red, versus one that uses an adaptive choice. So they propose a method that will quit the coordinate descent inner loop when it thinks it's done well with respect to the overall problem it's trying to solve. Then there's not a huge difference in terms of convergence. Okay, and the conclusion is really that this adaptive method that they've proposed, which actually kind of interrupts coordinate descent when it thinks that the progress is sufficient with respect to the Proximal Newton problem, not something that coordinate descent would know on its own, is the best one. So you don't get much worse from just doing 10 coordinate descent iterations, which is maybe kind of far from, or far-ish from the exact solution. But using this adaptive method is the best, both in terms of time and function evaluations. Theoretically, let's see if do I have the, yeah. So theoretically, this paper proves that if you have inexact function proximal Newton evaluations, so you use coordinate descent and you don't get the exact answer, which is what you should expect in practice, then the rate is locally superlinear, but it's not necessarily quadratic. So it's somewhere in between linear and quadratic. It's what we call superlinear. So I think it's still quite favorable. It's just not going to be the same blazing speed as Newton's method on paper, but superlinear is still a very fast rate. So this is, I think, probably the main contribution of this paper was to offer a rigorous analysis of what happens under inexact proximal evaluations. They also talk about, do I mention that here? Yeah, they also talk about proximal quasi-Newton methods, right, which was another interesting twist, which is what happens if you replace the Hessian with a low rank approximation to the Hessian using something like BFGS, which we didn't get to cover in the Newton's method lectures, but was at the end of the slides. And again, they prove that using a quasi-Hessian, like a low rank update to the Hessian, say using something like a BFGS rule, even with inexact noisy proximal evaluations, proximal Newton still gets local superlinear conversions. So it converges somewhere in between log of 1 over epsilon and log 1 over epsilon. Okay, so I wanted to finish with an interesting comparison, and apologies that this is not going to make a lot of sense to you if you've never heard of coordinate descent, but I thought it was relevant now, and we can come back to it after we learn coordinate descent. I can explain what coordinate descent is first. Let me do that, and then I can give you this comparison. So coordinate descent basically splits up a problem into blocks of coordinates, even individual coordinates, and then it iteratively optimizes along just each block at a time. That's what the method does, and how it does that is how it performs that kind of specific sub-optimization over a block of coordinates or a coordinate is it changes depending on the application, but you can imagine that for some problems I may be able to do that exactly. If I just ask you to optimize over one variable, you can figure out the exact solution for that variable in terms of the other variables in the problem. Or just a block of two variables, and there's a nice expression for how those two are related optimality to the other n minus 2. So block coordinate descent or coordinate descent just repeats that over and over again. So optimize over blocks of coordinates one at a time in sequence until convergence. Okay, so there's an interesting relationship between proximal Newton, where coordinate descent is applied to the inner loop, and what people sometimes call coordinate gradient descent, which I think is a bad name, but I'll call it block proximal Newton. So let's suppose that we're in this problem setting, minimize g of x plus h of x, where h of x decomposes into a function over blocks of variables. So for example, the L1 norm decomposes this way, where xb is just a single variable, right? Because it's the sum of absolute values of xi. In more generality, you may have your non-smooth function splitting up over blocks of variables. And Sang and Yoon have a very interesting paper from 2009 where they do something that I would call block proximal Newton. So they call it coordinate gradient descent. I don't think that's a very good name because it has nothing to do with, that name is not related at all to Newton's method. But here's the idea. In the Sang and Yoon method, you first write down this problem, and then the outer loop is over blocks B, going from 1 through B. And then the inner loop you apply a quadratic approximation to this function g of x, but only over xb. Okay, because in this inner loop, you're just focusing on optimizing the problem over a single block of variables, xb. So For example, for logistic regression with an L1 penalty, I would go to each coordinate. I would think about optimizing over that coordinate. I would look at the loss, the logistic loss, and I would make a quadratic approximation of that. That's not a one-dimensional quadratic approximation. And as a function of just, say, x1. And that's what I replace that with. And then I solve that inner problem. And I go to the next block of coordinates, make a quadratic approximation of the Hessian, but only over the, in the case of, like I said, logistic regression with an L1 penalty, only over x2. Now I'm just a univariate quadratic approximation. I solve that problem, and I go on, etc. That's different from proximal Newton. Proximal Newton is essentially the opposite order. If for the inner loop you use coordinate descent. So the outer loop, you apply quadratic approximation over all x to g. So over the full x. And then the inner loop, to solve the proximal operator, is the inner loop is that you iterate over blocks, say b equals 1 through b. So the opposite order. And I find that when I talk to people who solve these types of problems, where this is block separable and this is smooth, they often confuse these two. So people will tell me they're applying proximal Newton, but they'll actually be applying this. Or they'll be telling me that they're applying coordinate descent with Newton updates, but they're actually applying this. So these are not really distinguished very well, but they should be because they're different methods. These are not the same thing. So the quadratic approximation you get from actually approximating g over all the variables and then doing a block coordinate descent loop is not the same thing as first looking at a block and only looking at that block of variables and looking at quadratic approximation in that block. They are different methods. They actually have different guarantees. I think it's an interesting question as to what is the right order. I don't know if people have actually really studied this formally, but they both have good guarantees. They're just different methods. OK, so apologies if that made a little sense to you because you didn't know coordinate descent, but I think when we come back to coordinate descent, you can think about this example as well. So that was it. That wraps up our second order methods unit. Wraps up most of the kind of bread and butter algorithms we've learned in the course. And we're just going to do a review on Thursday to prepare for the midterm on Tuesday. So I'll see you then.